Halo, starlight, fades in light years. Children of light we are. Ammonia. Molecular formula is this. Structure formula is this. These two dots here are lone pairs of electrons in nitrogen, which can bond to an extra proton or hydrogen proton to form ammonium. So this is ammonia. Laboratory preparation of ammonium chloride reacts with calcium hydroxide, giving you calcium chloride, water, and ammonia. Okay, so the simple structure of this laboratory preparation of ammonia is down here, where you have this salt reacting with calcium hydroxide to give us ammonia. Calcium oxide, which is a quicklime is meant to dry the ammonia off of water, so the water vapor is captured here. It doesn't proceed to this point here. The ammonia is thus collected by downward displacement of air, or you can even call this one as upward delivery. Okay, I hope that's clear. So there's some heating involved here, which is the heat shown there. Physical properties of ammonia are pungent, sharp smell. Therefore, ammonia has a choking smell, less dense than air. That is why it can be collected like this, because it cannot go up, it will not come down, it can only flow downwards if it's denser than air, or if it's too much in the collecting vessel, it may flow out a little bit, but it will be trapped here because it will want to go up, but because of its less density, it will be trapped up here. Very soluble in water, liquefies at negative 33 degrees Celsius, and then it's colorless. Chemical properties, I've only given 3. You can still check for some more out there. So my first property is ammonia reacts with hydrochloric acid to give us ammonium chloride, which is a salt. This salt sublimates. Number 2, turns damp litmus paper from red to blue. Therefore, if this damp litmus paper is damp, it means it has water. So when the ammonia reacts or dissolves in the water on the litmus paper, it forms ammonium hydroxide, and ammonium hydroxide is aqueous, therefore it produces hydroxide ions, therefore it forms a basic or alkaline solution in the damp litmus paper. Therefore it's these hydroxide ions which cause the red litmus to turn to blue. The third one is ammonia in aqueous. Therefore if it's in aqueous, then it's actually in the form of ammonium hydroxide, which is actually a base. So this is a base because it's in aqueous. Reacts with nitric acid to give us ammonium nitrate and water. Ammonium nitrate and water. Those are the few chemical properties of ammonia. The Haber process. This is the industrial process of making ammonia. Nitrogen is obtained from air by burning hydrogen to remove oxygen, therefore leaving nitrogen. Therefore, hydrogen reacts with oxygen to give us water. What remains is a lot of what remains is actually nitrogen. Hydrogen is obtained from the reaction below, and that's our reaction. Methane reacting with water to give us hydrogen and carbon monoxide. This reaction is called steam reforming. Steam reforming. Conditions necessary for the formation, or in the Haber process, the synthesis or manufacturing of ammonia. You need to have an optimum temperature of about 450 degrees Celsius, optimum pressure of about 200 atmosphere, and then a catalyst, which is usually ion. The equation or the reaction through which ammonia is formed is as here, where you have nitrogen reacting with 3 moles of hydrogen to give us 2 moles of ammonia. This reaction is reversible, therefore it has the capacity to reach equilibrium. The diagrammatic arrangement of apparatus used in the industrial production of ammonia is here. It may come a little bit different, but it's here where you have the feed gas, which is nitrogen and hydrogen, entering the system, and the first component in which it encounters is actually the compressor. But remember, before these gases are even okay, let me not talk about that, because it will mean I'll have to talk about air, but they have already been obtained. Okay, I've already talked about the sources of these gases. So the compressor, the gases are compressed in the compressor. Compressing a gas increases its temperature. Allowing a gas to expand causes it to have a cooling effect. Therefore, compression is exothermic and expansion of a gas is endothermic. It absorbs heat, therefore bringing about a cooling effect. Gases enter here, they are compressed, their temperature increases. So after compression, the gases flow into the reactor. And this is my simple diagram of the reactor. I think next time I'll be using colored pens. Okay, colored pens. So in the reactor, the gases flow around up to the point where they enter into the heater, where they are heated. Therefore, the temperature is raised further. After the temperature is raised, the gases, which are nitrogen and hydrogen, pass through the catalyst beds. Okay, where the actual chemical reaction is made or enhanced. And at the end of it all, the products on the other end are going to be ammonia, and then you have some hydrogen and then nitrogen that remains after the whole reaction. So after the gas passes through here, it passes out going to the heat exchanger, and as it passes out, the gases are no longer hydrogen and nitrogen. The gases are now ammonia, hydrogen, and nitrogen. Therefore, part of the of the products are simply unreacted reactants. From the heat exchanger, the gases proceed to go to the condenser. In the heat exchanger, the cooling of the gas begins. The cooling of the gas begins, and the expansion actually of the gas is allowed because they were compressed and heated. Then, from being heated, they react. Then, cooling starts in the heat exchanger. Then, the gases proceed as ammonia, nitrogen, hydrogen. Okay, separately like that. They proceed to the condenser. The condenser has a water inlet and then water outlet. The water flows opposite. The water flows opposite to the flow of the gases in the pipes to maximize the cooling effect. Therefore, condensation takes place of ammonia. Condensation takes place and ammonia condenses and is tapped out of the reaction system, and then the unreacted gases travel back or are simply channeled back to the reactor. Therefore, they are compressed here and then passed back to the reactor. Here, this arrow should be like that. Passed back to the reactor where they are heated again and then pass through the catalyst bed, and then they form ammonia. And that's the whole cycle. And ammonia is kept on removed from the products for the reaction to proceed. And so you have the ammonia right there. Le Chatelier's principle. Whenever one or two of the factors that affect the rate of a chemical reaction are changed on any chemical system in equilibrium, the chemical system reacts to oppose the change. That is Le Chatelier's principle. Okay, whenever one or two of the factors that affect a rate of a chemical reaction are changed on any chemical system in equilibrium, the chemical change or the chemical system reacts to oppose the change. Remember, in my previous paper, I said this reaction is a reversible reaction. Therefore, it has the capacity to reach equilibrium. Equilibrium is simply a state where the forward rate and the backward rate become equal. Okay, the rate of change become equal. Therefore, equilibrium would have been said to have been reached. Okay, so reactions that are not reversible do not reach equilibrium because they go all the way from initiation up to termination. But for these kind of reactions, they are reversible, and there'll be a point when the rate at which the products are turning back to reactants becomes equal or becomes constant, and the rate at which the reactants form products becomes constant. Therefore, the two arrows are of the same length because they are representing rate of change, and at this point this reaction is said to be in equilibrium. So if you change any of either concentration or pressure, any of the factors that affect the reaction or the rate of reaction of a chemical reaction in equilibrium, you are actually, or the chemical system, the chemical reaction will actually react to oppose the change. Therefore, the equilibrium will shift to oppose the change that you have made. A note: the Haber process is exothermic and its yield is 15%. That is the maximum yield. Okay, max. So that is why ammonia is collected or removed, so that the forward reaction rate remains greater. Therefore, prevent equilibrium from being reached. The more you remove the concentration of the products, the more the reaction will not start reacting backwards, because if you allow the ammonium to accumulate, it won't accumulate to a percentage yield of 50%. You won't have excessive product. Therefore, it will just reach 15%, then it will start leaving. So for you to have the ammonia, you have to be removing the ammonia. As a result, the chemical reaction will simply keep on reacting to form more product, and you keep on removing the product. And so you won't give chance to lose the ammonia as it turns back to hydrogen and nitrogen. That's how Le Chatelier's principle is applied here. Other factors change to promote the forward reaction are increase in pressure, of course, which increases the when you increase pressure, the gas particles become in close proximity to each other. Increase concentration of reactants. Yes, you increase the probability of having particles colliding. Improve remove the product. Yes, optimum temperature. Therefore, increase the kinetic energy of the particles. Then use a catalyst, which is actually ion. Other chemical properties of ammonia are ammonia reacts with oxygen to produce nitrogen and water. So this is one way of producing nitrogen, although we have a lot of nitrogen in the air. Number two, copper 2 oxide reacts with ammonia to give us nitrogen, water, and copper. Nitrogen, water, and copper. Then lastly, uses of ammonia are in making nitric acid, making fertilizers, and as a cleaning solution. It's found in some of the cleaning solutions. I end here with ammonia. The next one will be the manufacturing of nitric acid. Remember to subscribe and leave your comments below. Thank you.